we introduce affinification, a method for accelerating elastodynamic simulations by combining elastic and affine models adaptively. Our approach uses a novel clustering algorithm to identify contiguous regions of the elastic model undergoing affine deformation. We use a metric based on the rate of change of the deformation gradient, and new elements are added to the affine region based on similarity to the deformation gradient rate of change at the centroid of each cluster. Affine regions of the model are coupled with elastic regions using a kinematic mapping that minimizes discrepancies between affine body velocities and the fully elastic degrees of freedom. Unlike rigidification, affinification supports non-uniform scaling and shearing, thus expressing a richer class of deformations with only a few degrees of freedom.
For example, here a beam is compressed and undergoes a shearing deformation, yet only a single affine region is needed.
Here we see that beams of varying stiffness benefit from our affinification approach. The stiffer the beam, the more affine the deformations. The benefits of affinification are evident as the element count of the elastic model increases. Randomly seeding our clustering algorithm outperforms seeding based on element order and temporal coherency, whereas the strategy for expanding clusters has a significant impact on performance. Our algorithm based on the deformation gradient rate does much better than naive approaches. This wheel deforms as it rolls across the ground. Using our affinification technique, the simulation is nearly 17 times faster than the fully elastic model and twice as fast as rigidification. Regions of this mattress that collide with the falling bowling balls are simulated using the elastic degrees of freedom, whereas large regions of the mesh can plausibly be simulated using our affine approximation. Here we see that affinification can be used to efficiently and stably simulate stacks of deformable objects. In this contact-rich scene, pill capsules are modeled using two different materials. The white half is soft and the green half is stiff. Watch them affinify as they fall down the distributor. Affinification, perfect for all of your mollusk simulation needs. Compared to the octopus simulated using rigidification, the affinification one is much softer, preventing improper rigidification of the tentacles. However, they can affinify, leading to enhanced performance. A jello meteorite is about to hit the Explorer 1 satellite. Thankfully, it elastifies on contact and leaves the stiff satellite affine, while the antennas elastify and wiggle about. A resource capping strategy ensures that a minimum of 33% of elastic elements are simulated using an affine or rigid approximation. The affinification motion closely resembles the fully elastic model, while rigidification appears too stiff on contact and introduces artifacts. Thanks for watching.